Okay, so I'm starting the recording, everybody. So welcome to our 1113 VCM lecture. And I'll go to the first slide. Again, I have some talking points that are of things that are on my mind. I'm going to start probably tomorrow trying to plan for the final exam accommodations. I'm spending a lot of my time on this. I just got an email from a student who was supposed to be taking the accommodation. They're claiming that they got kicked out. I told them I was teaching tonight until about midnight, and they say, that's okay, fix it after midnight and I'll be there. And so anyway, I'm spending a lot of time with that, and we're still doing the midtime accommodations. So thank you all for who were able to get that cared for, at least so we can move over, because I'm still doing that, and I'm going to be starting worrying about final exam accommodations tomorrow. And after all of those accommodations are done, then I can publish the midterm solutions. But in spite of all that, and with Linda's help and things like that, we're on track and on schedule. And tonight we're going to be talking about Chapter 7, which is an important topic. There are videos that you've already had an opportunity to look at and things like that. The topic is energy, potential energy, and kinetic energy, and we have multiple forms of potential energy that we're supposed to study. Also, in what we cover tonight is I'll be seeing what LSA, and this should probably said P5 because it's a physics one, but it has to do with Chapter 7, so we're going to see that tonight. So anyway, those are things that are on my mind, but I think on the whole and on the average, we're covering what we need to cover, and that's good. So teaching and learning is continuing, and we're on track and on schedule. And so, all of that as well, and those are the main things. Linda, anything you care to report?
We did have a very productive GSG session before class. I'm pretty impressed by what the students are doing outside, and I think they're going to do pretty well for the final.
Okay, that's really good to hear. So thank you for that report. Anything else, or does that hold you for now?
I think that's it for now.
Okay, great. And then I'll move to, if there's students' question and answers, and I'll count to 10 Mississippi before I move on. And anytime there is a student question, I'll start the count again after we try to address the student question. Okay, so I'm starting my silent count right now. Okay. I didn't hear anything, so we'll begin. Now, the things that we're going to do is I am going to be talking about, wait. Okay, so what chapters have we covered so far in physics? Well, and I'm talking about, the book of reference. We've covered chapters 1, 2, 3, 4, 5. Because 5, you see, 4 and 5 are really related, because one is about Newton's laws and the other one is called applications of Newton laws. So we've done those, and so we're through 1 through 5. And really, I've published notes, videos for you to watch on Chapter 7. Now, one reason I skip Chapter 6 is because it has to do with circular motion, and for the most part we don't need to do circular motion to understand the ultrasound physics. So I actually went through very carefully and picked the things that we need. Now, I am going to show you probably a problem tonight that if we had talked about circular motion, you'd be able to do the problem, and maybe I'll just mention that to give you a little insight about what we skipped. But it turns out when things are in orbit or going in circular motion, there are different forces involved than the ones we're talking about. But that was a conscious choice, and so we're skipping chapter 6, and chapter 6 wasn't included in the physics part, but chapter 7 is, and many other chapters are. So I would answer the question. We have done chapters 1 through 5 and 7 now. So that's my answer. We will go over several problems and talk about their solutions and so on and so forth. And this will also include the introduction of the Chapter 7 LSA, which I guess I'm going to be calling 5P whenever I post it. Okay, so let's, oh, here's something else. Okay, good. That just says that was a okay answer, I guess. Okay, so we're going to continue then with the next slide. So now this and the next several slides should be considered not a substitute for watching the videos I posted, but these are the kind of things that I will put in grace notes from chapter 7. And I thought, well, this is a good way to talk about some of the things that are there. Now, some of these I'm going to read to you. I'm going to point out equations, and we'll just talk a little bit about this. Okay, and I know I'm reading to you, but that's what I think is the best way to cover this this slide. And this is from the end of the chapter material in chapter 7. Energy is one of the most important unifying concepts in all of our physical science. And in fact, what really happens is it is important in ultrasound as well, and these are topics that are actively on the list for me to talk about: kinetic energy, gravitational potential energy, and elastic potential energy. And so we will be talking about those, and we'll also, before we're through, be talking a little bit about friction. Okay, so that's some things. According to the principle conservation of energy, energy is exchanged and transformed during interactions of systems, but the total energy in a closed system is constant. And we will use this to solve problems, because what will happen is that energy will change in between potential energy and kinetic energy back and forth, and then some energy will be dissipated by raising the temperature of things, or dissipated as frictional forces. So we're going to be talking about those kind of things here as well. And conservation of energy is another topic that's in our syllabus that I'm supposed to cover. So there are many, many, many of these topics that we're covering are very active things. Now, this chapter is concerned with 3 types, and these are called mechanical energy. Now, there are some energies that are not mechanical, but you want to think these being sort of moving parts that cause mechanical energy. And so we'll talk about that. But some things are not moving parts, like electromagnetic energy and things like that. And we'll talk a little bit about those, but not so much. Mostly we'll be focusing on this. So we're going to be talking about kinetic energy, and that's associated with the motion of objects that have a mass. And you see and even though electrons have mass in electrical energy, they don't have much mass. And so what really happens is you probably wouldn't even think about the mass. We will talk about gravitational potential energy, and that's gravitational interaction, and also elastic potential energy, and that's associated with the elastic deformation of objects. And in fact, what will happen in some of our work is that there will be elastic deformation of objects as well. So anyway, And let's see, potential energy can be viewed as a stored quantity that represents the potential for doing work. Okay, so there's a lot of words here and things like that, but we're going to be talking about all of those kind of things. So let's go then into a discussion of a different thing that is called work. And work, as you can see with it, is a, and I'll just read again, when a force acts on an object and the object moves, it undergoes a displacement. The force does work on the object and transfers energy to it. So for example, and this is an example that happened today for me at the College at DuPage, I climbed some stairs because I was teaching on different floors in the college. And so as I was roaming about the college, I would move up and down some stairs. And so what happened is when I climbed the stairs, I had to do work to climb the stairs. But once I did the work to climb the stairs, my body had more potential energy than it did before I climbed the stairs. So you see and I was working against the force of gravity to climb the stairs. Now this is the equation for, and I'm going to try, Linda, to grab a hold of my pencil here, my drawing tool, and it's not letting me do that yet. Maybe it has now. This, I guess, I hope you could see that line that I drew, Linda.
Yes, I can.
Good. Okay, great. So that line, that's an equation for what is work. And you see this says that work is equal to, and then there's that little F, and that is a parallel signal, symbol. It's like two lines, but F parallel is the component of the force parallel to the object's displacement of magnitude S. Now that's kind of a tricky thing, but I'll explain what that is, because you see the direction that I'm going matters, and this is only the force or the component of the force that's parallel to that. Now I often will tell a little story about this, and so I'm going to tell you the story, not to be telling you the story, but just to make the point. So you see, when my grandson was young, and he is not so young right now, he's a freshman in high school, and this is a story back when I used to pull him in his little wagon. And so this is what the wagon more or less looked like, and he would sit into that wagon and I would pull. But I would be pulling with a force, but here is the force that I was pulling along the tongue of the wagon. So you see my F, all my energy, my force, was pulling along the tongue of the wagon. Now, my grandson didn't really care so much about that, but in fact, let me tell you what he did care about. He really wanted to go fast. So going fast means the arrow was pointing this way, and that's the way he wanted the wagon to be going. So you see, he really didn't, and I'm going to erase this because I don't like the way that's showing up a little bit. So I'm erasing some things. And maybe I'll do a better job of drawing this with an arrow now. Let me see if I can do that. Maybe I can with this. Hold on. Okay, there's an arrow. So what happened is I was pulling his wagon with an arrow that was like this, going up in that direction. But that, as you know, is a vector. And so that means that that vector can be resolved in components. And one of the components is this one, that is the direction along the sidewalk where he wanted the arrow to go. And this was the arrow that also, and these two arrows, the one in the X direction and the one in the Y direction, add up to the one in the diagonal direction that was the tongue of the wagon. So you see, when we think about breaking things into components, we say, oh, we can understand this. And my grandson really didn't care about, and in fact, as far as he was concerned, I wasn't lifting this wagon at all, so that was wasted energy. So what I'm telling you is that in this, my grandson's story, the direction that mattered to him was this direction along the sidewalk. And so the only force that counts is this force. Now we'll go down and look at this picture then. Okay, so down here then, you can see, and I'm sort of drawing a big, circle around this, like this. So you see, the work is the force parallel times S. But if you look at this picture, you can see that the work going perpendicular to this, trying to lift the wagon, that doesn't count for work because nothing was really happening that way. This is the same thing as if I'm carrying a book and walking across a level floor. According to the physics definition, I'm not doing any work because the force of gravity is perpendicular, and the equation that you can see down here is that the force parallel is equal to the magnitude of the force, that was the hypotenuse, but it's times the cosine of this angle phi. Again, you say, oh, you mean trig is involved again? And the answer is, yes, it is. So work is only, it's force times distance, but unlike what you studied in high school, perhaps, it's not just force times distance, it's force in the direction of the motion times the cosine of the angle. And that's how you get in the direction of the motion. Okay, work is not a vector, it is a scalar quantity. And Linda understands that, and if you study enough math, you'll realize that this product actually is what's called a dot product, and it ends up being a scalar. So work is not a vector, even though force is a vector, and displacement is a vector. But when you take the product of the two, it's a scalar. And it points, well, and it can be positive or negative, but that's not a positive or negative direction. Either you can be adding work or taking work away. Now, when several forces act on an object, I'm still reading, the total work done by all the forces is the sum of the amounts done by the individual forces, but you take them all, making their components. So for example, if you look at this other picture that I did not make a circle around, but now I'm putting something around it, the work done by multiple forces is going to be the sum of them. But what happened is that if you think about people trying to push a car, and they're pushing it different directions, but it's only that's in the direction of the motion of the car, shown here by a dotted line, that matter. Now, if you think about this, and I've got to erase some of this stuff so I can write more on this, this chart. Later on, I'm going to talk about units. I guess I won't write a whole lot here. I don't know why it stopped erasing. I'll try it again. I really don't know why it stopped there. It started erasing again. But anyway, work is newtons times distance. So a Newton meter, a Newton, which is the unit of force, times a meter is a unit of work. But we call that a joule, and that is J-U-L-E. So that's some talking about work that is being done. Okay, now I think, just to keep this real and not be boring as a lecture, what I'm going to do is I'm going to go ahead and I'm going to come back to some more slides here, but I'm going to go and I'm going to do some other things first. And we'll find out if I have, and before I talk about units, and this is LSA 5, I don't want to talk about that yet. Let's see, this actually is going to be energy, so that is not work. And that's energy, that's not work. All right, here we go. This is problem 65. We will talk a little bit about this because this is talking about work. And this is talking about both work and power. And I guess we'll have to come back and talk about this piecemeal, but I guess that's the way I'm choosing to do it. So I want to mix this up so we're actually doing some work. So here's a problem, and I'm going to read it. The power of the human heart. The human heart is a powerful and extremely reliable pump. It truly is amazing. Many things about your body are amazing. We're talking about your heart right now. Later on, we'll talk about your ears, which are equally amazing, and your eyes are amazing. In fact, it's probably difficult to find a part of your body that isn't amazing. It makes one feel good about, there actually being some powerful divine intelligence somewhere. But anyway, the human heart is a powerful and valuable pump. Each day it takes in 7,500 liters of blood. And again, I should go up and try to get my pencil for this. Okay, so this is 7,500 liters of blood. And the work done by the heart is equal to the work required to lift all of that blood to a height equal to the average American female, who is 1.63 meters. Now, if you think about that, what they're saying is, and by the way, that's a lot of blood that's getting pumped around. A liter is very close to one of those 33-ounce soda bottles that you get drink. And so this would be 7,500 of those liter soda bottles. And so, those are big. This is a lot of blood that gets pumped around over and over again through your heart. And so what you're doing is, and you see your blood is pumped to the extremes. I mean, blood is pumped to your feet, it's pumped to your head. And so that's why they're saying that what we're doing is we're lifting all of that blood to your to the head of an average female, but it goes to their foot and to the head and everything else. So that's why they're telling you that that's the work that's done. But that's lifting 7,500 liters of blood, and that's a lot of work in a day. And so we're talking about that here. Now, they do tell us that the density of blood is just a little bit over, and blood is thicker than water, and the density of blood is 1050 kilometers per, and that's going to be cubic meter, because density is mass over volume. That's another equation that we want to know. And so the question is, how much work does the heart do in a day? Okay, so that's the question. Now you want to think about that. So we're lifting that blood, that distance, and so we're talking about the work that is done, and that's the equation we want to look at. Now, some of these questions, part B, says what's the power output in watts? We haven't talked about power yet, but we will tonight, and so we'll get back to that. And in fact, in part C, it says the heart puts out more power than you found in part B, and why. And we talk about that. We talk about what other forms do you give the blood. But what we're doing now is we're just talking about work. So the work required, the work that the heart does in a day when it takes in and discharges this blood. Okay, so let's go and look at a solution to this, and you'll see some of our equations in action, and you actually see the answer for this part A. And again, we'll have to go back and revisit this after we do this, but we're doing part A right now. So I go to this slide. Okay, well, here is the work performed each day. And so here is, and I have to go get my pencil again. And that, of course, covers it up, so I don't want to do that. So I'll click on the eraser, and I'll have to refresh the slide. I'll go backwards and go forwards again. Okay, now I'm just reading here, but please follow along. And I can't underline this because if I do, it hides it from me, so I can't see it. Okay, all right, so the work performed each day is work is equal to the work, but you might say, well, what force is the heart acting against? And it's acting against gravity, isn't it? So the force involved is gravity, and so what we have is that the work is going to be the force, but the force here is, and maybe I'll try to write some out. I'm going to try to do a little text thing, and that of course did cover it up. But F, capital F for force, equals ma. But the only acceleration in town is gravity, so this is m times g, the acceleration due to gravity. And again, I'm going back, and then I'm going to refresh the slide because it hides the slide from me when I do that. But you can see that F equals ma is equal to mg. And so now what we have is that m times g times h, where h is equal to 1.63. Okay, well, what we can calculate then is we can calculate the mass of the blood using rho, the density, which is equal to 1050 kilograms per meter per cubic meter. So that density is that number, and if I take that density times the volume, I'm going to get the mass of all that blood, and the mass of all that blood is going to be in kilograms. Okay, so what we do is we go down, and this is lower on the slide, so go on to the next page that I guess is called page 720 from the document I pulled this from. So going down to the next, and I really wish there was a good way to point here, but it doesn't seem like there is. Maybe I will try to use this now. I'll try to use my line drawing. So now I'm down here. Okay, so the work is equal to the work you're doing against gravity. That is mgh. But you see, m from this earlier equation was rho, which is the density, times v, which is the volume, which we have in liters, times h, which is in meters. Now watch the units that we have working here then, class, because, and I guess I have to get another one of these things up here. So now I'm going along here with the calculation, and I'm substituting all of those quantities in. So what we have is that the density is 1050 kilograms per cubic meter times the volume was 7,500 liters. But you see, I've got a problem because liters doesn't cancel with the cubic meters. So I have to change liters into cubic meters. And I do that with a conversion factor of 1 cubic meter per 1,000 liters. So now what happens is the cubic meters cancel and the liters cancel. And now what I have is kilograms. So that is kilograms. That's good. Okay. But then I'm taking kilograms times g. And g is the acceleration due to gravity. That is 9.8 meters per second squared. Now everybody should now understand what I have is now I have kilograms times acceleration, that is force. But so you see that's a kilogram meter per second squared. But a kilogram meter per second squared is what we called a Newton. So you see that is a Newton. Now I take the Newton times the 1.63 meters in that direction, and I multiply all those numbers together. The units end up being kilogram meter per second squared times meter, but that's a Newton meter. That's called a joule. So I do that calculation, and this is what I get for the work. And the answer to the problem then is that this is 1.26 times 10 to the fifth joules. And that's a lot of work that the heart does in a day. Okay, now I'm going to put out some questions about that, but that's the work done. And so we did talk about work now, at least as something, and now we can go back and talk about those other things and perhaps return to this problem to talk some more. Now, Linda, you listened to that explanation, I hope, you and Seven, and I'm not going to ask Seven to explain it, but I might ask you, is there anything more that could be said or that seemed to be unclear in that that you would want to clear up in the discussion?
I don't think so. I think you went pretty in depth.
Okay, so thank you for that, and we'll say that that's good, but I want to pause for a count of 10, Mississippi, to see if students want to ask questions, because I would expect you to be able to do a problem like this. Yes, Amber.
So towards the end, when you're changing it to joules, you said that was I'm trying to figure out how to word this. Kilogram meters squared, that equals joule.
Okay, I'm going to say my thing again, and I have a slide that's called units,
Okay.
but no, I'm not telling you. I'm going to answer your question now, but I'm just telling you that I'm probably going to say some things. I'll either repeat then, or I'll get to that point and everybody will understand, and I won't have to. Okay, so here's what's going on. And this goes all the way back to all kinds of things that we've studied. And much of what we're doing is building up horsepower in terms of units. Okay, so I'm going to type some things here trying to answer your question, Amber. And while I'm typing and saying them, they're not going to show up. But when I'm finished typing, they will show up. Okay, so we know that work is F time is force times distance, period. So force is newtons, and meters is distance. Yes, somebody typed the same thing that I'm typing. So meters, and thank you for that. And meters is distance. Okay, so work is Newton times meters. Okay, now I'm going to click off so you can see that. Okay, so, and I typed some words there that I hope you can see. Linda, you can see my words?
Yeah, we can see it. Thank you.
Yeah.
All right, good. Okay, great. Okay, so work is Newton times meters, but we have a name for Newton times meters, and it's named after a great physicist who did a lot of work on thermal energy and things like that. And this guy's name was Joule, and it was J. Okay, thank you, Linda. Okay, so this is Joule. That's the way you spell this guy's name, but that's a unit. So a Newton meter is equal to a joule. Now, Amber, I'm going to tie it into this problem, though, in the following way, and I'm going to be writing another thing, and this is going to be F equals ma. That's Newton's second law, so F equals ma, so I'm typing F equals m mass. I keep trying to type the m and I'm not getting it. Here we go, ma. So that is a kilogram. And then acceleration happens in meters per second squared, s squared. This would be so much easier in a classroom on a chalkboard. Okay, so that's kilogram per meters per second squared. Okay, so, and of course that said D equals ma instead of F equals ma. That was supposed to say F equals ma. And so a Newton is a kilogram meter per second squared. So if you say, well, what's a joule? A joule is this thing, which is a Newton, kilogram meter per second squared, times another meter. So this is a kilogram meter squared divided by second squared. Now, if you look at the calculation we just did here, Amber, a lot of units canceled out, but the things that didn't cancel out were kilogram meter squared over second squared, which is a joule. Now, I'll probably say some more about this later on that other slide, but that's my attempt, Amber, to answer your question right now. Did that help? I hope.
Yeah, it helped. Thank you.
Okay, so that's units. Okay, so now we're going to go back and talk about some more things, but at least we've talked a little bit about work, so maybe that was useful. I think that is useful. Okay, so we're going back to these things. And this is work, and we're finished talking about this slide. So that's all I'm going to say about work, although there could be problems about work. But now I'm going to move on, and I'm going to talk about work and kinetic energy. Okay, so here we go. And kinetic is a Greek word that means motion. And so kinetic energy, sometimes, I know the words don't say it here, but sometimes kinetic energy is called energy of motion. And when you see the equation, you're going to say, well, of course it's motion. Okay, so now I'm reading. The kinetic energy, K, of an object is defined in terms of an object's mass, and this says its speed, V, and here is the number for kinetic energy. Okay, so I'm going to grab a hold of that thing, and I'm drawing a line under the equation. Now you're going to have that equation available for you in the grace notes, but you have to know what to do with it, okay? And Amber, please follow along with this. And by the way, Amber, I'm not accusing you of not following along. I'm just saying the discussion that you and I had that you claimed was useful and helped you understand it is really going to help you in what I'm going to do right now, okay? I think. So kinetic energy is 1/2. Now 1/2 has no units at all. So it's just 1/2. Then it has mass, and mass has units of kilograms. Then you got velocity squared. Well, velocity comes in meters per second. So Amber and everybody else, the units on kinetic energy then are going to be kilogram meters squared per second squared. But kilogram times meters squared per second squared is the same thing as a Newton. Meter is the same thing as a joule. So what are the units of kinetic energy that comes in? Joules again. And Amber, I'm not trying to, pick on you or ram that down your throat, but did that make sense to you? Do you see how that we're forced for the units of kinetic energy to be joules also?
I think so.
Good. All right. And we're going to probably revisit this a little bit later whenever I get to that units slide. But the point is that kinetic energy is, and by the way, this is called energy of motion because if you're not moving, your velocity is zero. So if your velocity is zero, you have 1/2 times your mass times zero. Your kinetic energy is zero. So this is the energy associated with motion. And it's going to be, the equation is 1/2 mv squared. Okay. Now, when forces, I'm reading it again, when forces act on an object, the change in its kinetic energy is equal to the total work done by all the forces acting on it. Now, this is called an energy theorem in your book. And what I'm going to do is try to get a hold of my pencil. And I'm going to draw this equation here because this is an important equation. And this equation is said that the total work done is going to be and then you see it says delta K. So the total work done is the change in kinetic energy. So it's going to be, so the total work is the change in kinetic energy. And you see they say it is the final kinetic energy minus the initial kinetic energy. So let's do a couple of examples. So here is a Honda. And the Honda has mass of 1,300 kilograms. And the velocity of the Honda is 2 meters per second. So, and you might say, well, what work was done? Well, and by the way, I do drive a Honda, okay? And sometimes I drive it faster than 2 meters per second. But anyway, what happens here is that when I drive my Honda, what work is being done? The engine is doing work, isn't it? It's moving the car. And so what happens is the work that the engine is doing, so like suppose that my car is parked there, but I go out and I get my car started up and I start driving it at 2 meters per second. Well, the work being done is being done by the engine of my car, and it's causing my Honda, which has a mass of 1,300 kilograms, to be moving at a velocity of 2 meters per second. And how much work is being done by the motor on my car and it's doing work on the Honda is the kinetic energy, which is the kinetic energy is 1/2 mv squared. So if I take 1/2 times 1,300 kilograms times velocity squared is, and when you square 2, you get 4, and you get meters squared per second squared, you end up with 2,600 joules. Now I'm going to pause and count to 10, Mississippi, in case people want to talk about that, because we've actually done something now with that kinetic energy formula. Now we're going to do something else. Now, I do not have a Mercedes, but I have neighbors who do. They spend their money on different things than I do. But they have a Mercedes, and the Mercedes is a much larger car than my Honda. In fact, it is twice as large. It has twice as much mass. But how much work is the Mercedes engine doing to take the Mercedes engine from being at rest, not moving at all, to moving at 1 meter per second? And you can see it's 1/2 m times v squared. Now this time v squared, the only thing you're squaring is the units, because 1 squared is 1. So this is meters squared per second squared, but we get that. So you see my Honda, in doing this task on the left-hand side, is doing twice as much work, and my car has twice the kinetic energy of their Mercedes at that time. Okay, I counted to 5, Mississippi, and no one asked a question. Now I'm going to go try to go find a problem where we can actually do some of this things about kinetic energy. So let me go and look at some of the problems that I picked here to talk about. That actually has kinetic energy in it, but let me go back to okay, now again, I'm doing bits and pieces of problems because I think it would be boring to do it the other way, and so here. But a typical human, if you leap out of an airplane, you reach a terminal velocity of 62 meters per second. Okay. And a person, and I've got to go back so I can see the rest of the slide because of this. All right, so a human reaches 62 meters per second. Okay, if a 70, okay, so I'll go down and pick up this part of it. So if a 70 kilogram person reaches the ground traveling at the terminal velocity of 62 meters per second, and I'm asking a different question here, but what is his kinetic energy when he hits the ground? Okay, so you got a person jumped out of an airplane. They are 70 kilograms, and it reaches the ground traveling at a terminal velocity of 62 meters per second. Okay, well, the answer to that is going to be, and we would have to do this calculation. I think Linda is tied up right now. And so what I'm going to
No,
do
I'm
is,
back.
okay, great. Linda may, I'm going to write some things here, but Linda may pound this into Excel or use a calculator. She probably has a calculator there. So anyway, I'll let her speak to what the number is in a bit. But you see, if a 70 kilogram person reached ground traveling at a terminal velocity of 62 meters per second, and we know that the formula is K is equal to 1/2. Kinetic energy is 1/2 mv squared. Okay, so this is the mass. 1/2 is 1/2, and so you will include that in the calculation. M and v squared, now this was kilogram. I'm going to talk about the units for the most part, but this is 62 meters, but it's 62 meters per second, and these are whole squared. So I'm going to be talking about units a bit here, okay? And so let's talk about the units. So the units, 1/2 has no units, it's just a number, but I have kilogram, but then I'm squaring this meters per second. So that again, and Amber, I'm not picking on you, I think you asked a great question earlier, but that's kilogram meters squared per second squared. But kilogram meters squared per second squared is joules. So the unit on this is going to be joules. And by the way, to get a feeling for this, this would really hurt. If you jumped out of an airplane and were going 62 meters per second, that's really pretty quick, and that would really hurt you when you hit the ground. You probably would sustain significant injuries, and you might actually, it might be fatal, depending on what really happened with the ground. But anyway, perhaps Linda will either have done this or something. But the units are going to be joules. And Linda, what does the number come up to be?
That is 134,540.
Okay, so that's a big old number. That's a lot of joules, isn't it? And in fact, we could compare the joules with, and we're not going to, but if we were in a classroom, we might go back and say, hey, is that how much work your heart did during the day, or which one was more? But this kinetic energy is hurting you, and your heart is keeping you alive by putting blood circulating through your body. Okay, so anyway, that's another example of kinetic energy. Okay, so let's go back then to some more of this lecture. All right, and that's probably enough about kinetic energy. So kinetic energy is the energy of motion. And again, I really encourage you to watch the videos because there's a lot more examples that I do in the videos and things like that than I'm really able to do in this class. But that's energy of motion. That is called kinetic energy. Now, sometimes forces vary. And so what happens is there is a little discussion of work done by varying forces. And what this basically says is work is area under the curve. Now, Linda knows calculus and things like that. And actually, there's some pretty fancy math here, but Linda knows how to find the area under that curve using calculus. We're just giving you equations, and we're not requiring you to do calculus, but you are going to have to remember additional equations. And this talks about another one of them. This is called Hooke's law. And you see, if you take a spring and you stretch the spring, you have to do work to stretch the spring. Or if you shove the spring, if you compress a spring, you're also doing work. And so here are some concepts that you want to know about here, even if you don't know how to compute the area under the curve. And this will be elastic potential energy. And we're going to look at a problem that does this in just a bit. So if the magnitude of the force required to stretch or compress a spring a distance s from its natural length is proportional to f. It is proportional to x. So that means, and I don't like the way that covered up what I was trying to do, so I'm going to just erase it, but that's where I am. This is called Hooke's law, and this is, again, another one that you want to know about. But Hooke's law says that the force is equal to kx, where k depends on how big the spring is, and that's called a spring constant. And this is, so the force is directly proportional to the compression or the extension of the spring. So there you've got a force. but you're also moving it through a distance. Okay, so this then is an equation for the total work needed to stretch a spring from x equals 0 to little x equal capital X is W. And here's a formula. This is a different formula than the one we had before. This is W equals 1/2 K, where K is the spring constant, times X squared. Now, it turns out that this comes from calculus, where the 1/2 and the X squared comes from. And Linda's probably good enough to teach you that, except she's got other stuff that she's teaching you instead of teaching you that bit of calculus. But that is what happens there with that. So you see, we have another form of work, and again, the mathematics can get quite involved, but we're asking you to know that formula. Now, it turns out, though, that this work that you're doing, this becomes potential energy, not kinetic energy. And we'll talk about that. And you might say, well, when are we going to talk about that? We're going to talk about that right now. So now we're going to talk about potential energy. And again, I know I'm reading to you, but you guys have these slides in front of you so you can read them, and we'll read kind of along. And by the way, there are several videos, and they're much longer than this lecture is. So potential energy can be thought of as stored energy. It's stored energy. For an object with mass m, and this is called gravitational potential energy, and of course I can't see that because I can't draw on top of that. So I have to go back and refresh the slide. The gravitational potential energy is mg, you're working against gravity, times the height, or the distance you go in the y direction. Now, just to give you an example, and I'm looking ahead, about kinetic energy, I'm going to try to do a drawing, and here is my drawing. So suppose this is a BIC building at the College of DuPage, and I went up, well, let's see. Linda, how much does your calculus, well, I don't want to say that. I'm just taking an apple that weighs, I'm taking a hunk of meat that weighs 1 kilogram. I'm going to the top of the BIC building. So those are my legs, and that's my arms. My arms really are not that long relative to my legs, but I have this sack of meat, and this meat is 1 kilogram. And I took it up to the top of the BIC building. Now the BIC building has a height, and I'm holding this at some height, and the distance from the ground to where I'm holding this, I'm calling y. So you see, that has a potential energy. And you might say, well, it doesn't have energy of motion because it's not moving. I'm just holding that sack out there. But because of its position, it does have potential energy. Hold on for a second. I'm lecturing. I'll call you back in a bit. Thanks. Bye. Okay. Okay, so I have some energy of position. But what happened if I let go? And Linda, just so I'm having somebody to talk to, and Seven might not respond to me. When I drop this, does that hunk of meat start moving?
I mean, I'd like to hope so.
It sure does, because of gravity. And so what happens is this hunk of meat starts moving, and it's going faster and faster and faster as it goes down down to the ground. Okay, so what's happening is the potential energy that I have up here, the gravitational potential energy, which is mg times h, is being changed to kinetic energy, which is 1/2 mv squared. So we do have something called gravitational potential energy, and there is the definition of gravitational potential energy is right there. It's mgh. Now, and again, and Amber, I'm not picking on you. You ask a great question, but think about the units on this. M times G is newtons. The height of the big building is in meters. That's a Newton meter. That's a joule, isn't it? So mgh is joules, but that is gravitational potential energy. And what happens is that the gravitational potential energy in this case is changed into potential energy, and we have the conservation of energy, and we'll talk a lot about that, and we'll do problems like that. Now there is another kind of, oh, and here's an example of it right over here. This is gravitational potential energy. So if you lift up, and this is not a hunk of meat, this I think is supposed to be a book, but suppose you lift up the book, and you lift up the book from the ground, which we call Y final, up to a height above the ground called Y initial, and then I let go of it, what will happen is the book will fall. Its weight is m times g, and it will hit the ground. And so you see here again, the gravitational potential energy is being changed into kinetic energy. Now, there is another form of gravitational, or another form that we want to talk that is called elastic potential energy, okay? And that is beginning to talk right here. So when a spring is stretched or compressed a distance x from its uncompressed length, the spring stores elastic potential energy. For example, if Linda were, okay, Linda is leaving for her class now, her meeting. Okay, so what happens is if you pull, and I'm glad she mentioned that because I would have forgotten that tonight, if you pull that spring out and let go of it, it bounces back, doesn't it? That means there's some potential energy causing it to have energy of motion. And similarly, what you have is if you push the spring in and you let it go, it will spring back out again, boing. For example, when you sit on your bed, your mattress, if you have springs in your mattress, it will crush the mattress down because you're laying on it. But then if you get up from the bed, those springs will push the mattress back up. So you see there's another thing called elastic potential energy, and that is this this equation right here, which is 1/2 k x squared. Okay, so 1/2 k x squared, and that k again is the spring constant. I talked about this on an earlier slide. So that k is the spring constant, and what happens is that is and that x squared, that is the potential energy that the spring derives from being pushed in or pulled out. This is called elastic potential energy. Okay, and again, the lecture is probably much better in the videos because I'm following along with a narrative and I got some good figures. But you see, that's what's happening here. Then this drawing here shows if you're pushing that spring in and letting it go, you see that what you get is that for a spring stretched or compressed by a distance x from its equilibrium point, the elastic, that's what that EL stands for, potential energy is 1/2 k, the spring constant, x squared. Now I'm going to go and show you a problem I ask on the physics exam. And so you say, oh, I probably want to make sure that I know how to do this. And the answer is yes, you do. And this is the problem that we're looking at right here. And this was a full problem on the final exam. And I'm not going to say I'm going to ask this one, but understanding this would be a really good thing to know about. So, and you got a little bit of a picture here. So a 1.5 kilogram box moves back and forth on a horizontal frictionless surface. Now friction, and you might say, you mean they're frictionless surfaces? Not really, but and we'll talk about friction later, but friction makes things harder, okay? So you got this box that's there, and so what happens is, let's read more about the box. So 1.5 box moves back and forth on a horizontal frictionless surface between two different springs. The box is initially pressed against the stronger spring. And by the way, if I look at this, I'm showing you what the spring constants are. So the spring constant for the spring that you see on the left is 32 newtons per centimeter. Now what that means is to compress or expand this spring, you have to introduce a force that is equal to K, where this is K. This is 32 newtons per centimeter that you compress or expand this. So that means that spring is twice as strong as the dinky little spring on the right-hand side, which has a spring constant of 16 newtons per centimeter. Okay, so what that means is that it's twice as strong as a spring. So you see what you're doing is you're taking this box and you're shoving it into the spring on the left-hand side, and you're compressing it 4 centimeters. And you're holding it there for a second. But then what you're going to do is you're going to let go of it, aren't you? Yes? And when you let go of it, what's going to happen is that it's going to start moving, isn't it? The spring's going to start shoving the box is going to start moving, and in fact, the potential energy of the spring is transferred to the box. And so the box picks up some kinetic energy. And then what happens with the box is it runs into the other spring, and the kinetic energy that you're having, the energy of motion, starts pushing this spring in, and so it pushes that spring in, and it's a different force. And in fact, one of the questions that's being asked is, so we'll go back to the story again. So the box is initially pressed against the stronger spring, compressing it 4 centimeters. Then it is released from rest. But then it goes all the way and bangs against the other spring, and it compresses the spring. So one question that's asked is, by how much will the box compress the weaker spring? How far will it press it in? That's question A. Question B, and this is exactly the problem that I asked on a final exam once, what is the maximum spring the box will reach? Now that's speed, because there is speed in the middle, because all the potential energy of all the elastic potential energy of the spring has been transferred to the box. So the box is riding along there at 1/2 mv squared. Okay, so we have to figure out some of this stuff. Okay, and so that's the problem. Now I think what I'm going to do, and Linda's not here to do the calculation with me, but we're going to talk about, okay, so how would you do this problem? So I'm going to start sharing a whiteboard with you. And Amber, I'm not picking on you, but you're one person I know that's out there. Amber, memorize a few of these numbers for me, or write them down or something. So Amber, one of the numbers that we're going to need is 1.5 kilograms. That's the box. Actually, I'm pretty good at numbers. I might remember all these, but just in case, Amber, and I might not call on you unless I have to. But this is 1.5 kilogram box. Okay, it pressed against the bigger spring, which was 32, and it did it 4 centimeters, and then the other one was 16, and it asked how much will the box compress the weaker spring, and what's the maximum speed the box will reach. So I'm going there, and Amber, I don't know if I'll have to call on you or not, but if I do, you'll know those numbers and can help me with the numbers. Okay, so here we go. Okay, all right, and I am going to use my pencil this time, and I think this will be just fine. Okay, so you see what happened is the left spring was compressed, and so the energy, that is potential energy, when this was compressed is going to be 1/2. The spring constant was 32, and it was compressed 4 centimeters. Okay, so the potential energy then, and this was 1/2, that was 32, and that's 4 centimeters. And so the potential 1/2, that's 16 times 4, that is 64 is what we have. Okay. Now this is transferred to the box, but all this potential energy starts the box moving, and then the box hits the other spring and it pushes it in. So all this potential energy gets transferred to the other box, or the other spring, excuse me, the other spring. I'm answering part B first, but this is going to be 1/2, but this was a dinkier spring, so this spring constant was 16, and the thing we wanted to find out was how far is it compressed, and so I called that S in this diagram. Now if you look at this, you can see that there's only one um, um, there's only one kinetic energy here. And so what we're going to do is we're going to, and I think that was 16, but what we have to do is we have to do this calculation. And let's see, that was 4 centimeters, right?
Yeah.
Okay. All right. So we'd have to solve this to find out how much, so the potential energy gets there, but we would just have to solve this. Now, what also happens is that this 64 was transferred to the 1/2, and I think this was 1.5. So this is 1/2 times 1.5, and this was velocity, and this was squared. So that's 1/2 mv squared. And so I would have to do this, and this would, I'd have to solve this for velocity. But you see, this is how I would do a problem like this. And I will, in fact, show you, we're almost finished for tonight, but I'm going to go back to, wow. I guess I can share my screen. This is a little tricky because I'm not 100% sure how this is going to work, because I don't want to share the whiteboard. I want to share my application screen. And maybe I had to stop sharing and start sharing again to do that. I do have the solution there for that with the number. That's loading the whiteboard. So what I want to do is stop sharing this and share my application screen. So I'm doing that. So I'm sharing this. And now I'm going to, I guess, PowerPoint, and I'm not seeing where Linda was with the PowerPoint slide. Anyway, I do have the solution to that there. Okay, so that brings us to the end of the end of tonight. But you've got the videos to watch, and we're really finished with Chapter 7 from a lecturing point of view. We'll do a little bit more of it in the VCM next time, but we talked about potential energy, both elastic and gravitational, and we talked about that. So this probably will make the videos, or rewatching the videos, even more useful. So good night, carry on, and everyone please be careful. Good night.